think about, twirling the thing around your head. String breaks to my right, meaning your left. And so the question is, in the process of doing it, the velocity, again, we haven't really discussed it quite so much, but it has a direction and a speed associated with it. So if the string breaks right here, at the point at which the string breaks, the ball is pointed basically directly perpendicular to the string. So they're going outwards. Because usually what you experience when you're going around in a circle, okay, in particular, say you're in a car, and you're going around a curve, right, sitting in, on the passenger side, the car is curving towards the left. What is it that you feel? If the car is going really fast. What's that? Yeah, basically, you feel yourself being pushed against the wall, right to the right. Okay? And most everybody knows this, right? Now, so this is the real problem. And so the reason why people will say, good fraction of people will say to the right, is that it feels like there's a force there, and so if the ball is going around here, the string breaks, it's just going to go to the right. Okay? Second most, the peak answer is number 2, which is to go straight ahead. That, in fact, is the right answer. We'll discuss about that in a minute. Number 3 is the spiral outwards. Again, that's the idea that basically that there's kind of a force associated with it, so it tends to push it outwards. The idea is that the force, which is keeping the object moving in the circle, is essentially the string pulling on the pulling on the ball, right? No string, no force on the ball, right? The only thing that keeps that ball moving in the circle is the fact that the string is there, okay? String breaks, no force, right? And so the question is, from Newton's first law, if there's no real force, what's the only force on the ball once the string is cut? Gravity, right? It's got its weight, so eventually it's going to fall to the ground, right? But that's the only thing that's there, and so there's no force basically in the horizontal direction, right? And so there's nothing, it will basically keep on going on that trajectory forever, right? In other words, the direction won't change. It'll come in, the velocity is perpendicular to the string, going this way, and so it'll just go straight back, straight along. And so that's the reason why 2 is there. We're going to talk about it again, okay? But it's a good demonstration or an example of Newton's first law in action. So, okay, this is about as good as solid a rhythm as you're going to get, right? In other words, it's equally just like the clock, right? That is the essence of a constant speed, right? So in other words, it travels at equal distance. Each one of these 40 centimeters now, it travels exactly the same distance amount of time. So it's like a clock, okay? That is a constant speed. And so if I were to measure, it's approximately, I don't know, what would you gauge, about half a second for each one? Then it's going basically 20 centimeters about half a second. You take 20 centimeters, you divide by half a second, and that gives you about 40 centimeters a second. Maybe. Okay, get the idea? Now, and we now, instead of being flat, we now put gravity into the problem. Okay, and again, this is what Galileo did in order to talk about inertia. So, same thing, okay? Like every time it goes through, you pass one of the markers, every now 4 centimeters, 40 centimeters. Now, I'll start it from rest. Okay? That is acceleration, right? Because in other words, you can define the velocity. What did you hear, right? The interval gets shorter and shorter as it goes. It accelerates, right? It's the way even in music you talk about accelerating tempo. And so the idea is that the distance that travels between those markers is exactly the same, but the time it takes to go past those markers decreases as a function of time. So in other words, you can define an average velocity between those markers, and it's the distance divided by the time, and so the velocity that you define increases as a function of time. Therefore, it accelerates. And that's all that there is. Okay. We first have to get the ball started going, and then it goes up the ramp. Okay? same deal. It doesn't quite get up there. It actually turns around. Let's talk about energy. Okay, but you get the idea of what's happening here, what's happening to the speed. It's increasing, right? Because the time interval increases for each one of those intervals, right? So the speed is decreasing. Is that an acceleration? Yes. Okay. It's just that it's in the reverse direction. And acceleration also is what's called a vector. It has a direction associated with it. And so actually the acceleration in the opposite direction of where the ball is moving. Okay. Then the velocity decreases. Just kneel on the carpet. This basically is a fish scale, which essentially is a spring. And it's a fairly strong one. This one can go up to about, I don't know, 30 pounds or so. About 15 kilograms. Okay. Right, so it's gotten harder and harder. But what this allows you to see, you might have to grab on it pretty hard. And so the idea is that this allows me to always continually putting a constant force on it. You very rarely do this, okay? Because usually what happens is it goes faster and faster. You don't want to keep on pushing it harder and harder. So in other words, if I have it going at about this, what you'll notice, of course, is we're going to have a wreck. All right. You get the idea? But you saw it, right? It goes faster and faster. There's no real problem with that. I guess you have the bearings all the way backwards. I'll try not to tell you process of moving. I wish I had a bit more wide open area. But the point is that I can actually go down to about 2 or 3, 4 pounds. And so I can actually do it keeping exactly at about 4 pounds. And what you notice is that I can still manage to keep it going pretty well. Right? It's actually hard to keep it exactly constant. The acceleration is lower, but as long as I do it for long enough. Thank you very much. Let's give him a big hand. The idea is that a small acceleration acting on, in other words, I put a small force acting on it for a longer period of time, I will eventually get to the same velocity. Now the other difficulty though is, suppose I do this forever. I apply a very small force as long as I want to. Thousands of years. Okay. What does it do to this law tell you? The acceleration is constant, and so the velocity keeps what? Going up and up and up and up and up, and there's no bounds. So eventually you could push it hard enough, you can go all the way across the size of the universe in a second. Right? Okay. That's next quarters. Because the point is that it turns out that Einstein, this is not possible. Okay, and so Einstein's special relativity says it's not possible because it tends to violate causality. Weird things happen if you go faster than the speed of light in very strange ways. So it's not possible to have it happen. What really actually happens is that it goes faster and faster, is that the inertial mass actually increases. And in fact, it diverges. So in fact, no matter what you do, all the work that you go into doing, it just makes the particles heavier and heavier. Completely bizarre. I won't go into it. It's never happened in real life. That's why I don't do it. Okay. Always dangerous to sit in front, but I'll try not to. Okay. But those of you who want to try this at home, right? The idea is that what you can do is that you can drop the banana and slice it mid-flight. Okay. This essentially is exactly what this is what it's saying, right? Okay. Now the problem is I don't know whether the knife is sharp. This is a really, really cheap knife. Okay. And I had a really nice knife, but I lost it. So we'll try it. Okay. But the idea is that what's going to happen as it goes through. As I cut through it, what's going to happen? Is it going to go flying to the wall? No. What's the difference between, say, if I drop the banana versus dropping a block of wood? So if I did drop the block of wood, what's going to happen to the block of wood? It's going to go flying off, right? The idea is that somehow it's the difference of the force that's required to cut it. Okay, and because it's a really ripe banana, okay, it does not take much force to cut it. And so if I'm lucky, right, I can actually do it.